Alright, hi everybody. I just wanted to make some videos kind of going over these free response questions because I think they're kind of difficult and pretty tricky. So what I want to do is go over this first one. So we say, okay, we have this disk, it spins about the axle, and the student does an experiment and we find that we have a constant torque acting on this disk. So what we're doing for this first part, again, sorry of this, I didn't say sorry before, but sorry for this format. I know Google Forms are not ideal for this, but it's something, I guess. It's no pen and paper, but whatever. So we're saying, okay, at time t equals 0, the disk has an initial counterclockwise positive angular velocity omega naught. The disk later comes to rest at time t equals 1. So this is not too bad because we've done stuff like this before. What we're saying is we have a constant force acting on it, a constant torque acting on it, which means that we have a constant angular acceleration. So we know when we have a constant angular acceleration, we're going to do that one first. Really, we have something that is acting to slow us down. So we know it's going to be negative. It is acting against our positive initial uh, angular velocity. This is in the positive direction, and if we're slowing down to come to a rest, we know that we have to have a negative angular acceleration. So that's pretty good. So we know that it's constant because it tells us that in our situation. And then what we know is, well, when we're going from acceleration to velocity, the slope of our velocity versus time graph is just going to be the same as the value of our angular acceleration. So this has a constant negative value, which means our slope is going to have a constant negative value. That's supposed to be a line, so let me kind of do a better job with that using all my tools. So that is a constant negative value that should stop at 0, but I kind of overshot it a little bit. Sorry about that. Oh my gosh, maybe this ruler wasn't a good idea. I figured if I have the tools, I may as well use them. But yeah, whatever, you get the gist. All right. Now what we're saying is the magnitude of the frictional torque exerted on the disk is tau naught, so this initial torque. Derive an equation for the rotational inertia I in terms of tau naught, omega naught, and T1. So what I can do is I'm going to start and say I want to know about the rotational inertia. So I'm going to write my equation that I know about rotational inertia. I know that the value for that is somehow based on the mass and distribution of that mass. And I also know that I have this equation that's like kind of my Newton's second law, but for rotating objects. So instead of F equals ma, I have torque equals I times alpha. So in this case, we have a value for torque. We know that it's this torque naught. We want to find I, and we don't know alpha. So this really tells us, hey, we're pretty close. We know this and we're allowed to use it. We want to solve for I. If we can just get something to tell us about alpha, then we're going to be good to go. So let's think about what's happening here and what else we're given. So we know that we start off with some initial angular velocity. We know that we're going for some amount of time. We know that we want to find alpha. And then another piece that is not really given to us up here, but we do know that the final angular velocity is just 0. This thing comes to rest. So if we're looking at this, we kind of have this omega, omega naught, t, and alpha. We have an equation for that. We have this equation that says omega equals omega naught plus alpha t. So let's set this equation up, but based on what we know. So we know that it comes to rest. So our final velocity, our final angular velocity is 0. Our initial is still this omega naught. This alpha is what we wanted to solve for. We said that we needed alpha if we want to solve for I. And then this t is t1. And one thing I'm also going to do is just say, hey, I know that the acceleration is negative. I know that it's working to slow it down. They're acting in opposite directions. So if I want to solve, I can say omega naught equals alpha times t1. And alpha equals omega naught divided by t1. Then I can take that alpha, plug it in, say torque naught equals I times omega naught over t1. Then if I want to solve for I get tau naught t1 over omega naught is equal to I. All right, so that's our first one.